Hello, good afternoon. This is Oscar Hernandez, and today I'd like to give a short talk about a paper that I reviewed for a class, and it was titled Model Inversion Attacks That Exploit Confidence Information and Basic Countermeasures. I want to give, first of all, material acknowledgement and credit to the authors M. Fredrikson, S. Jha, and T. Ristenpart for this paper that they wrote. And this paper explores how attackers can reconstruct private training data from machine learning models' confidence outputs, and they suggest simple ways to reduce this leakage. There's also other references that I've added in there, in addition to some outputs from a experimental that I ran using the suggested codes. Okay, motivation and background. So what a little bit about this. These modern machine learning models often output class probabilities, call them confidence scores, and the attackers can use these probabilities to deduce sensitive features about training examples. Their goal is to understand here in this paper the vulnerabilities in sharing confidence scores and to propose basic defenses. And a key point that is being made is that sharing detailed confidence information can inadvertently reveal private training data. And why is this important is because it threatens an individual's privacy. What are some of the concepts of a model inversion attack? Um, in this type of attack, an adversary queries a trained model to recover information about its training data. And the idea is to exploit these confidence scores and to see how close you're getting to the class that you're trying to estimate. Um, Inverting a model is essentially reconstructing an approximate or partially accurate version of the training sample. For example, face recognition, uh, or if you're trying to find other like financial information, health information, things like that. The key point is that MIAs can reveal personal or proprietary data from a machine learning model's output distribution. Uh, in the picture shown at left from the article that I was am referencing, the blurred image is a recovered face, and the image on the right is actually the target face unblurred. So a little bit about the threat model. In terms of attackers' capabilities, there's two general types. There's black box access, where the attacker has access to the confidence scores or predictions, uh, and that may be all. But in a white box type attack, the knowledge of the architecture, the parameters, partial knowledge of the training distribution for the data, the test data, the training data, that would be really good in helping to make a prediction. The target model, typically, it's a classification model with multiple classes. And a key point here is that even limited black box access can be enough to mount an effective attack, for, in other words, an inversion. Attack overflow view. What happens is you begin with querying the model with different inputs, collect confidence vectors returned by the model. You optimize or iteratively adjust inputs to maximize confidence for the target class, and you obtain a reconstruction version of the original training data. And the key point is the attacker's main handle is the confidence information on every query. And so through this iteration process, you're getting closer and closer. It's kind of like a hot, cold thing. And you're getting closer to the information that you'd like to extract. An example is domain face recognition. Uh, often used as a real-world example. Machine learning models can classify which person is in a photo, and the attacker attempts to reconstruct the facial image of a known user in the training set by systematically tweaking input images until the model's confidence in that user's identity is high. The key point is high dimensional data, like images, for example, can be partially reconstructed from confidence feedback. And there shown is a class reunion type photo. And it'd be interesting to see if you could do correlations between what was 50 years ago and what is now 50 years later, and to make those estimations, just as an example. Baseline model inversion attack algorithm. You start with a random noise image or a generic average face. Then you apply gradient descent or iterative refinement. You query the model, measure the confidence for the target identity. You adjust the image to increase the target class probability, and you repeat until you get convergence. And the output is the final image approximates the target's facial features. And the key point being, this model uses gradient-based or search-based approaches to invert the model. The iterative scheme may also incorporate constraints like facial plausibility or smoothing to ensure the reconstruction looks realistic. And this is sort of add-ons that you're doing in addition to these other extraction type code that's being added. Exploiting confidence information. Why does it matter? Well, fine-grained probabilities reveal the model's internal boundary preferences, class boundaries, and other such type information. The difference between class probabilities helps guide the attacker's refinements more accurately. So if you know how that model works, and if you can create another pseudo model, well, okay, then you can start writing your own. The risk is the more detailed the probabilities, the easier it is for an attacker to zero in on private features. Key points there: detailed confidences accelerate the inversion attack's convergence. And one thing to guard against is overfitting, because that can memorize the training data and thus making it vulnerable. Experimental setup from the paper. Well, they had data sets. LFW was one of the suggested ones, Celeb A, or other standard sets, the models, CNNs, other specialized classification models, evaluation matrix, similarity or accuracy measures of the reconstructed image versus the real image. In other words, I'll talk a little bit more about that downstream, but those are what you're using to help make judgments. The key point is the paper demonstrates effective reconstruction on standard base benchmarks. Two surveys that were discussed in the paper were the 538 survey and a survey called GSS. And in one, what they were doing was they were discussing stake preferences versus an individual's risk behavior. And in the other one, they were talking about marital happiness. And so what accuracy, there's white box with the most best results, but ideal, that's what you'd want to. But there's black box, there's random, there's baseline type approaches. But the biggest concern is if you took this this survey anonymously, it can be reverse engineered to display your tendencies. One of the questions, for example, was, has there been marital infidelity? And I can see if that got out well and then got back to the other partner, that could lead to a divorce. It's pretty risky. I'm not saying it's appropriate, but I'm just saying this is something that how it could evolve into a negative way. What are some of the attack variants examined? There's gradient-based optimization, genetic algorithms, or other heuristic searches, composite imaging techniques. And the key point is that multiple approaches confirm that confidence-based feedback is enough to systematically invert the model. from denoising autoencoders to softmax, and then there's a sample of the algorithm shown from the paper. Sorry about that. My image is partially blocking it, but it is available in the paper itself. In terms of results, you can have successful reconstructions with partial resemblances to the actual training images, impact enough detail to identify the person or reveal sensitive attributes, performance, good results under various model architectures. This is a good one. And the key point is even partial image recovery can be a serious privacy risk. In this example from the code that I executed, you can start to see the outlines of a face and hey, it's starting to take shape. And so with more epochs, other tweaking of parameters, it gets even better. So what are some of the root causes? Well, overly detailed probability vectors that leak information about data distribution. Uh, the model may be optimized for classification accuracy, but not necessarily for privacy. Many machine learning systems do not incorporate any mechanism to obfuscate or limit confidence outputs. The key point is, by design, classification models output signals that can be exploited unless mitigations are added, and these form the basis of why these attacks can succeed. What are some of the proposed countermeasures? Well, okay, so I'll be talking a little bit about confidence masking and rounding, dropout at inference, regularization or noise injection, limiting output to the top one or to the top K class, when you're providing information. And the key point is the paper proposes straightforward methods to reduce leakage without heavily altering the model's architecture. In countermeasure 1, rounding, the idea is to round the probabilities to the nearest 0.1, for example. This likewise causes the reduction of granularity of that feedback attackers can leverage. There is a trade-off, of course. Slightly less fine-grained feedback for legitimate users is there, but it significantly hinders MIA's precision. The key point is rounding is simple and can be applied post-training. Countermeasure number 2 is dropouts at inference. Randomly, you drop neurons during inference, similar to training dropout, but used at test time. As far as effect, the model's confidence output is more noisy, making it harder for an attacker to get stable gradient signals. There's naturally a trade-off, and this potentially reduces classification confidence for legitimate tasks. But the key point is it introduces randomness, making repeated queries yield inconsistent outputs. And that is a good way to deter. Countermeasure number 3, noise injection, kind of as the initial seed noise shown at the left. In this approach, you add random noise to the confidence scores or internal representations. This degrades the attacker's optimization signal. And you have to choose noise levels that's, call it high enough to thwart an attack, but not too high to break a model's utility. And in terms of key point, it's another straightforward technique, but it has to be carefully tuned. I mean, you still have to keep the model working for the true users. Countermeasure 4 is the top K class truncation. Here, only release the predicted top K class or top 1 or 3 class information and you hide the rest. The rationale is that if the adversary sees fewer confidence scores, there's less data to exploit. Consider releasing only quanti-score ranges such as medium, low, high versus detailed knowledge. Trade-off. The users lose the advantage of seeing full confidence distribution, which may be important for certain tasks. But the key point here is that simple but effective, especially if k equals 1, is the only predicted label. And so this avoids returning a detailed breakdown of the model's confidence across all classes. So you're limiting output. In my example, I use 4 of 7, but hey, I'm just trying to get going there. What are some of the effectiveness of countermeasures? Well, results from experiments show how each countermeasure degrades the attacker's ability to reconstruct an image. As shown at the left there, at the rounding equal to 0.05, the attack does not produce a recognizable image. That's the more blanked off sort of black image there. Typically measured by structural similarity or mean squared error metrics between reconstructed and real images. So these help to assess the attack's effectiveness. And even basic rounding or top K can significantly disrupt inversion attacks. The key point is no single measure is foolproof, but they collectively raise the bar against MIAs. And in the bottom part of the table at the bottom is showing some of those metrics of MSE and SSIM, the mean squared error and the structural similarity. In terms of performance versus accuracy trade-off, well, there is an accuracy impact. Some minor drop in model performance occurs if the output is heavily altered. Utility versus privacy, you got to find an acceptable balance. From a user's perspective, for many applications, a slight accuracy reduction is acceptable to preserve privacy. And the key point is perfect privacy is impossible without impacting utility. This is about managing trade-offs. So this is a consideration when you're working in this type of environment. So what are some of the recommended best practices? 1, use minimal confidence information, only as necessary for the application. Employ basic countermeasures like rounding or top K. Evaluate attack risks regularly with new MIA methods. Combine multiple defenses, okay, top K plus noise injection, rounding, these kind of things. The key point is a layered defense approach can mitigate various forms of MIAs. Well, there are ethical and legal implications. Biometric data, face, fingerprints, medical data, financial, personally identifiable information, it's sensitive, and for a good reason, because it can lead to fraud or discrimination in some ways, whether in insurability, getting a loan, this sort of things, even hacking and causing other types of theft. There are regulatory pressures that have to be adhered to. In the European Union, it's called General Data Protection Regulation, and this is to protect a person's personal data and the privacy of their citizens. In the US, we have a similar framework. Just one aspect of it is the Health Insurance Portability and Accountability Act, HIPAA. And, we often see these sort of things breached. And, it's a constant battle there. There is an ethical duty. Machine learning researchers and system developers must consider potential misuses of shared model outputs. And the key point is the consequences of data leakage can be severe, reinforcing the need for protective measures. Limitations of the proposed defenses. Adversaries can be most adaptive, and they can use advanced techniques to counter basic measures. In terms of model complexity, some defenses might not generalize well to all architectures, for example, large transformer-based networks. Unintended consequences, over-rounding or high noise might degrade legitimate use a little bit too much. And the key point is these are basic defenses, not a guarantee against all future attacks. Here in the lower image, we can see the face of Ariel Sharon emerging. This is based on the algorithms and code that was provided for this project. And in the histogram shown, what you're trying to do is you're trying to get them similar. And so this is considered actually pretty good. Comments on limitations. Well, there are some. And if you optimize confidence in the target class, it's not perceptual realism. The attack often converges to adversarial patterns that trigger classifications, but don't necessarily look like faces. Remember, the model wasn't trained to generate images or classify them. That's why inversion from noise can fail visually. In other words, you're trying to classify is what I'm trying to say here. And if you're basing it off the probabilities, the confidence scores, that's what you're after. And then from there, you can infer backwards. Comment on analysis tools. Heat maps show a per pixel absolute differences between the original and the inverted images. Bright spots show strong differences. Uniform areas mean low change or noise. And it's useful to visually localize where inversion failed, but more so where it is successful and has succeeded in capturing an image as shown in the heat map shown on the right. And this is something that I came across as I was trying to debug the code and get it operational. So what are some of these metrics? Well, structured similarity index, mean squared error, peak signal to noise ratio, histograms, original versus inverted comparisons, and difference heat maps, which show the pixel-wise absolute differences. And overall, in the test I performed, it went pretty good. And some of the numbers are shown. They do adhere to these ranges as it's recommended to get a successful attack. So what are some future directions? There's advanced privacy mechanisms, differential privacy, homomorphic encryption, hybrid approaches. There's robust testing, call it penetration testing, regularly auditing models for vulnerability to evolving MIAs. The key point is long-term solutions may require deeper changes to machine learning pipelines and more advanced privacy-preserving machine learning methods. What are some of the key takeaways? These model inversion attacks can exploit confidence vectors to reconstruct sensitive training data. Simple approaches such as rounding, dropout, noise injection, regularization, top K class release, they offer notable protection, but you have to balance utility and privacy in choosing these countermeasures. And the key point is awareness of MIA threats is essential for anyone deploying ML models that return detailed confidence scores. In conclusion, confidence-based MIAs pose a real privacy threat. They're simple yet effective countermeasures that can mitigate these risks without drastic performance loss. Adopting even basic measures goes a long way to safeguarding training data privacy. So, anywhere a model learns to map inputs to outputs, there's a potential vector for inversion if enough information is disclosed. And in the top right is some outputs that were discussed in the paper. You have your target, and then you have a softmax, and then you have your denoising autoencoder output. And so these are some example. And then your multi-layer perceptron. And they all kind of succeeded in a way. So that's kind of showing that these attacks can be quite effective. Thank you.